So for some of them, yes, but for some of them, no. Integrals. We're reviewing. I have a New Year's resolution. Well, our whole family adopted it. 1 hour of screen time a day, and 2 hours on the weekend.
No, I was on TikTok for 7 hours a day.
Tell me what, are y'all looking at your screen time?
Yeah.
All right, so tell me what an integral does. It's the area under a curve. That is exactly right. What does that mean? I'm right. Lizzie made a terrible face. It's the area under a curve. So by a curve, I just mean any function that I'm given. And we'll get into some three-dimensional stuff here soon, and you'll see. So if I wanted the integral between these two values, right, what I'm doing is I'm finding this area. And if it's in a shape that you know, in other words, if I had, let's say it was a linear function, y equals x, y equals x, and I wanted the area from x equals 0 to x equals, we'll say 2. Then what is that? That area is a very familiar shape. That's just a triangle. I could just find the area of that triangle, right? But the problem comes, so this area, 1/2, of course based on height because it's a triangle. And I don't remember if we talked about this as much. Yeah.
We did rectangles, I think, going this way.
You actually can. That's when, and that's a more advanced technique of differentiation, and that is with respect to y instead of respect to x. You know how we took the derivative with respect to different variables? That's with respect to y. We will get there, but it'll be a little while. Good question, though. Good question. Yeah, you are. Did y'all hear the question? Because that's a really good question. Why we take it? Why our rectangles are vertical instead of horizontal? Because we're with respect to x. So our bounds are with respect to x instead of respect to y. All right, so if it's a familiar shape for us, it's really easy to find the area under on a certain interval. But if we're something like a parabolic curve, it gets a little harder. And so that's where we use our rectangles and we cut it up into a certain number of rectangles. And then we find the area of each rectangle and we add them together. Do y'all remember doing that now? You don't remember how? Okay, let's do an example. And you have the problem on your calculator too. Y'all remember that, right? Hmm? Unless it's a non-calculator, in which case, let's see. Number 17 in your book. Let's do that. Let's do that one together. Oh. Okay. So integral, derivative is the rate of change at any specific point, right? It's the slope of the tan line at any specific points, the instantaneous rate of change. The integral is the area under the curve. Right, and so right now we're talking about definite integrals, which means a definite interval of values. So between 0 and 2, or from 2 to 5. We will get into indefinite integrals where we'll find the area under the entire curve for all of infinity, and those are a little bit harder. But right now we're working with the definite. Yeah. Does that make sense so far? Okay. So number 17 gives you a t-chart of values, and then it graphs it for you. And so I'm just going to sketch it here. It starts at 2, and it looks something like this. And this is cardiac output. And since the following table gives dye concentrations for a dye concentration cardiac output determination, like the one in a prior example. The amount of dye injected in this patient was 5 milligrams. Use rectangles to estimate, and so this is the time is on the x-axis. Martin Luther King Day. And this is the dye concentration. And because it gives us this T-chart, and if y'all, if you want to look, you can, but you don't have to. We're going to use those values to help us as we find these rectangles. This goes up to 24, it looks like, is where it actually, it doesn't hug it, it kind of stops right now. We want to use rectangles to estimate the area under the curve from 2 to 24. Maybe in that top right drawer of my desk if you want to go look. So there's not a certain number of rectangles here, so we're going to use our best estimate. And if you were looking in your book, there's a table. Let me just give y'all the table. Be a little easier. They will a lot of times. They'll tell you what they want your end to be. Do what? Right. Yeah. Yeah. Or they'll say 10 rectangles of equal width or something like that. All right, let's see. I just want y'all to see this table so we can switch back and forth. All right, there's the table. Actually, there's the table and the chart. So if I'm looking at this graph and it didn't tell me how many rectangles to use, so what do you think would be a good number of rectangles to use?
We should use the number that, like, just number of units.
I would agree. I would use the points that are there for us. You see what I'm saying? So, and think about this in number of rectangles now. So this starts at 2, and then it jumps to 4, right? But that's one rectangle. Okay. Thank you, Bill. How many intervals should I use here? 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? Do we all agree 11 would be a good estimate here? All right. Ready to do the math? We're going to let in be 11. You don't, but for this one you can't. Why can't you use your calculator on this one? There's no function there. There's no equation of a function. That's how many intervals you want. N is your number of intervals. Dylan, yeah, but look, it just gives you the. So what should we do? It doesn't say. It just says use rectangles. So which one would I probably not want to use? MRAM. Why would that? Well, it's the median. It's a little more accurate than the other, but at the same time, then I'm going to have to calculate midpoints for everything if I do that, and then right? So midpoints. So we'll start with left RAM, and then we'll do right RAM, and we'll compare them and see what happens. Okay, so as we divide this up, if I do left RAM, golly, I can't even write today. It starts with the leftmost endpoint. If this is my interval to here, it would go to here, right? And that's my rectangle. And then this rectangle. So it measures from the left point of the over to the next interval, right? But if I do right RAM, we'll do both. It won't take but a minute. Well, for right RAM, my very first interval, if they're 2 units long, right, I'd go here to 4, find it here, and then go backwards to the endpoint. What happens? And you really don't even, it helps you to draw a picture because it helps you to kind of see it. But you don't need the picture to do the calculations, because once you pick up the pattern of it, it becomes really easy. Because what's the area of a rectangle? The area of a rectangle, you forgot. Length times width. My width is constant for every single rectangle. Do you agree? What's changing? The length of the rectangle, right? The height of that rectangle is changing. But every single time, if I'm going from 2 to 24 and I have the 11 units, right? What's the width of each rectangle there? 2. Did I see that? Okay. You have already asked me that, and I am not doing that really. Okay. If you just need to find the width of your rectangles, okay? To find the width. I'm trying to think how I could word this since we haven't done specific yet. Let's do the x max minus the x min divided by your n, which is your number of intervals. So in other words, for the one we're doing, we're going from 2 to 24 on x, right? Say right, because that's right. Okay, so 24 minus 2, 22, would be 2. So my width for all these is 2. Does that make sense? You could, but sometimes they'll get. Sometimes you'll have like decimals and stuff, and they'll get a little bit harder to see clearly. You know what I'm saying? It won't just be one unit. They might say, like if I said do this with 25 equal intervals, you'd be like, oh well, it's divided by 25, right? Yes. All right. So mine, hers, mine, mine's 4. I like it because y'all always have 4th block free. Well, most of you have 4th block free. Do y'all have 4th block free this semester? Huh? Get what? Really? Area of each rectangle. We know that the width is the same, so the area, let's say just of this one. Let's just look at one, and then we'll kind of generalize here since y'all wanted to review a little bit. Area would be the width of 2, right, times the height. How am I going to find the height of that triangle? Not triangle, right. It's not necessarily. Look at the chart. You're exactly right. So depending on if I'm doing left ram or right ram, depends on which one I need to start with, right? L ram would start with 0, right ram, and it would go until this point, right? Do you understand why? L ram, and then right ram would start with the point 6 and would go all the way to the end. Does that make sense to y'all? No. Okay. Okay, look at the picture. So, and let me pull this. Let me show you. All right, left ram. So left ram, this would be the corner of the triangle, right? I mean the rectangle. Golly. Right? So, and then it would come over to here. Right, it wouldn't be right. Well, but you want to include it just to be in the habit of including. You see what I'm saying? Because if you're given a table, this is more than likely what you'll do something like this. You'll have a table, and then you'll have to know what to do, right? So I would start with 0. Well, then the next rectangle, which starts at 4, would measure, the top of the rectangle would measure to here, right? Well, that measurement is 0.6. And I would keep going, but when I get to the end, I wouldn't need this one because I'm measuring from the left end, not the right end. Does that make sense to you? But if I did right ram and I switched that up and I started at 4, this would be the height of my rectangle. This would be, and I would stop it right. Okay, so let's do them both because they're really quick. Once you pick up the pattern, they're really quick. So this would be times, I'm going to say times f of whichever x you're using. But what we'll do is we'll say the whole area, and we'll do left ram. The height's the same each time, right? So I'm just going to pull that outside and say, instead of saying 2 times this one plus 2 times this one plus 2 times, I'm just going to say 2 times, and I'm just going to add them all up. So left rem, I'm going to start with the 0, right? And I'm going to go 0, 0.6, 1.4. Those are the ones I'm adding to. Y'all see? It is. Okay. Yeah. Sorry. 2.9. I ran out of room. What? No, because I don't have a calculator up here. And I'm going to stop at 0.5 because I don't want that last point. If you get it as a multiple choice. 22.4 without the double. I mean, did you multiply by 2? All right, so this differs from the right ram because if I do the right ram, of course, right ram just changes. I'm going to be really lazy right here. And I'm going to say, but if you would like to rewrite, you want me to rewrite it? Okay, I'll rewrite it. Leaving out that. So instead of starting with 0, I'm going to start with 0.6. Do you really, Dylan? Well, just so you have it in your notes with. Not here. Somebody explain to me why the right ram and the left ram are the same in this. It's symmetrical, but also this is kind of what you were fixing to say about the what happens when you get to the, I think this was what happens when you get to the top. Whereas on this side, right, it was giving me an overage if I was right ram. When I get to this side, a right ram would give me an underage, right? And so we talked about this just a little bit, and we said if the function is increasing, y'all probably don't remember this. I remember briefly saying it, but I don't think we. If the function is increasing, which it's doing until I get to that maximum, right? Then right ram gives me too much or too little? R ram would give you, if it's increasing, so this side, as the function increases, right ram gives you too much. Too little. But if you flip that around and your function is decreasing, of course those flip also.
It is. At the top when it starts going down.
Right. So once you've hit the top, my function's no longer increasing, it starts decreasing. All right, do you need just a second before we do volume? That was just a recap of prior to. It's, yeah.
We never got the bottom of this.
What?
We never got the bottom of this.
I know. Yeah, you don't want to do the bottom of this one. We found area. We found the area under the curve here. 44.8. Yeah, we just had this whole conversation. Okay. How? What are you talking about? Dylan, are you serious right now? Difference in volume and area. Right. Three-dimensional, two-dimensional, I add an extra specification in there, right? I got length times width versus length times width times height. So what if I asked you, are y'all ready for this? This is such fun. No, it's not even going to be, no. You're going to have to visualize this, so I'm going to probably show you the picture in here first. But let's say I asked you to find the volume of a sphere with a radius of 4. And we're going to do this using RAM. We're not going to do this that you could just look up how to find the, I know. Let me show, I think it'll be easier for me to show you the picture. This is not the easiest thing, but don't fret. Because we will get to volumes of rotation and stuff, and then we'll come back to this and you'll be like, oh, duh. It's not as hard as optimization. I don't think so, no. All right. Volumes of rotation really are about being able to visualize what's going on, okay? So what we're going to do, if we want to find the volume of the sphere, we're going to break this up into pieces. If you look at it, really all I've got are different circles here, right? Instead of triangles, I'm using circles. Y'all with me? And then I'm just going to add each one together to find the volume of that sphere. Yeah, engineering. It's not puzzling me. I'm just trying to think if I should hold off until we get to volumes of rotation and do this all together, or I did this first last year. It went well.
Yeah, how did they do? Like, did they do good?
Because it's an easier example of rotation and gets you into your. But it's not really rotating. It's just. Let's just walk through it. We'll see how you do with it. All right, if I've got a sphere, let's think about this on a coordinate plane. And I know that's two-dimensional, but let's just think. I'm going to we'll go to 4. The radius is 4, which means the diameter would be 8, right? So I'm going to think about this semicircle here. Terrible semicircle, but you get the point. What is the equation of that semicircle? Okay, well, how do you find the equation of a circle? Just 2D. The equation of a circle. No. Good morning.
How's everybody doing?
Good, how are you?
Back. Woo!
My center's at 0, so that makes it easy, right? H and K, okay, so Y, but because this is my center, right? So it's just Y squared because my center's at 0, 0, because it's, sorry. Okay, let's go over the equation of a circle. Equation of a circle. I got this backwards, don't I? I should have put the H and K the other places so that it would be HK was the center. But if I'm centered at 0, 0, then I'm just Y squared plus X squared equals R squared. Because my H and my K are 0, right? Okay. So if you had to write the equation, y'all got that? Of this in terms of Y, what would you do?
I would plug in the radius.
All right, we know the radius. We know the radius is. So I got y squared plus x squared. Do you agree with that? But that's the entire circle. You agree with that?
Do we need to put a 2 under the 1 next?
Why would you put 2 under? Is there something with a square root? Solve it for y. Solve it for y and what happens? Minus x squared. So why does it not have the bottom of the circle if that's the equation? It's still I didn't take, you're right though, I only took the primary root, so I didn't take the bottom of it, right? If I had solved this and I had thrown my plus or minus in the front, that minus, that would be the bottom of my circle. Are you all with me? So when you write it this way, it includes the plus or the minus of both parts. That's why it includes the top and the bottom of the circle. But if I solve it with square roots and I solve it for y, I don't take the negative portion of it, so it doesn't include the bottom of the circle. This would just say, just keep the primary root. Does that make sense? Okay. So this equation would be the square root of 16 minus x squared. Yes. You have to plug in the center into, right. This is like y1, this is like x, or I should say yc, xc. Your x center and your y center. But because it's 0, it made it a little easier. They would, that's why I said I should have wrote it y minus k and x minus h, because y'all are used to hk being. Oh, you mean flip sign-wise? Technically, yes. I should have written it like that. It is, which is 0, 0, so it's irrelevant. You okay? All right. Now what are we going to do? We're not going to add the third dimension. What would make sense? How many intervals would make sense to break this into? You think? 4? So 8 altogether, maybe? Why is that the most feasible number of intervals? Each width is going to be just 1, and that's going to be an easy number to work with. Do you agree? So I'm going to let n be 8, which is going to make my width 1. Now remember, I'm talking about volume, so I'm talking about. Which is divided by 8 would give you a width of 1. What? Say it again.
Yes. Okay.
All right.
You're here, I'm here.
That's right. That's what I say. Just saying. We all got to come to work. With our, if I start cutting this, and I'm talking about volume, so I have to start thinking 3-dimensionally, right? So as instead of pulling out rectangles, what I'm really, taking out are these circular pieces. Does that make sense?
Yeah.
How would you find the volume of a circular piece?
What's the volume?
The area of the circle times.
What times is that?
No. Times the height, times that width each time, that height or that width. Right, that's the only difference in volume. Anytime I'm having the volume, I'm just adding that. It's the area times that extra variable. Okay.
Wouldn't I do the same thing?
No, but when you start saying, I think you're thinking right, Because you're thinking diameter this, but since we're talking about a circle, if we start saying diameter, we start thinking about I don't know.
So what is the little?
Well, what is the little? You know that. What is the little width? But what is it? What's the value? It's 1 every time, right? So every single time, that's the constant, right?
So no one's
The radius, right? If I want, so if I take this one piece here, if I pull that out, right, I've got this circular piece, and I need to know, and I'm going to use,
basically just the diameter can be
right, because it asks for the volume of a sphere. Yes, yes. Okay. All right, are y'all with me? So, what? I told you this is so different. All right, do we agree to find the volume of one section that's taken out? I wish I had something that I could just pull that out and show you. All right, I'm going to do the area of the circle, we know to be pi r squared, right? Times that constant width of 1. Does that make sense? Are y'all with me? Okay. That's the area of that sliver, right? So I'd have to do that for every single one. At this point, I would probably have a calculator, and I would probably let the calculator handle, well, you don't have a RAM program yet. You just have rectangular RAM. Okay, never mind. Right. That's correct. That's correct. So let's look at it. Let's find one, and then it'll make it a little easier to go through the others. All right, so each time, this is what's changing, right? And that's my function itself, do you agree? Because radius is half of the diameter, so from here up, do you agree? I could do it from the left, the right, or the midpoint. It doesn't really matter. And I could actually do half of it. I could... Okay. Let's do, well, because I could do it from the left side or I could do it from the right side. So, because, all right, remember, all right, here's 1, 2, 3, 4. Mm-hmm. All right, so my little pieces, right, and I went way above, I shouldn't have. You could use the radius from the left side or the radius from the right side. It's still the right and the left deal, right? Do you see that? Are y'all with me? Okay, so let's just pull out one of these circles. And we'll go left. You see what I'm saying? Because when I measure, right, we're going to have to go MRAM. I know y'all are going to hate that. We're going to have to go MRAM on it. We're going to have to go midpoint because we're talking about this circular. To get the true value of this circle, we're going to have to go in the middle here to find it for the radius. Right. Well, because this is a circle, not a rectangle. Remember? And it's volume. Okay. So I know this is tough, y'all. Just stay with me. I'm sorry. This is a lot. It's not, but it's the right. So instead of plugging in 0 or 1 for my x value, I'm going to have to plug in 0.5 and 1.5 and 2.5 and 3.5, right? But if I can just find half of this circle, I can double it because it's symmetrical, right? So really, I only need to find the volume of these 4 circles, add them together and double it, and I'll have the volume of the entire thing. Does that make sense? Okay. Remember this equation. What's this equation? No plus or minus, just the plus. Square root of 16 minus x squared. That is the function. I'm finding the area under, well, the volume under, essentially what I'm doing. All right, so let's look at this very first piece here. The volume of that very first circle, or that slice of a circle there. Pi. What is r? How'd you get it? R is 4 for the entire sphere, but not for my little piece that I'm pulling out. Okay, so 0.5 is where I'm measuring from. So if this is my circle, right, to find the area or to find the radius of that circle, I'm going to go from the center and I'm going to find where it lands on this semicircle. How do I find that? So I plug, yes, that's exactly right. So essentially what I'm doing is the square root of 16 minus 0.5 squared. Does that make sense?
Why plug in 0.5?
All right, because I want to go mid-range. I want to go from the midpoint, right? The middle of the interval, which is 1/2. So what is the value of y on the circle? Because this is my radius, and that's what I need to find for my equation is what's my radius. So the radius is the distance from here up to the semicircle. We did the same thing when we were doing, here is the value of the function, right? It's just that this is a nasty function. Yes. So if you came over here and you said, okay, well here y equals the square root of 16 minus 0.5 squared, which is 16 minus a quarter, which is 15 3/4, 15.75, so square root of it, but you're squaring here. You could. If you want to add it up for each one here and then plug it in, you can. But I want to make sure here, remember, I've got to take that third dimension into account here because it's volume. So this is, I'm just going to put this in a bracket here and say each one is times the 1, just so you don't forget that you've got to add that in there. Say that again. Because that's what since that was the radius of the sphere, that's what's bounding it. And so I know that to find that radius, because my circle does this number, right? You've kind of got to be able to picture it. I can't draw it as well as what these are this way. Well, here's your semicircle, right? So from the middle of any interval up to here, you just plug in that midpoint value to this equation to find where it lands. Does that make sense? Okay. I don't know. You got to do it on calculator. But I'm going to keep doing it because I'm going to do it. This is just for circle 1.
I usually do like 1.5, 2.5.
And if this is right. Yes. And then, that's right, don't forget to double it at the end because we just did half the sphere. So then I'm going to add it to, then I go to the next one. Well, this is 1.5 instead of 0.5. So this is pi times the square root of 16 minus 1.5 squared, pi r squared. Plus, and then I go to the next one, which is 2.5. So pi times the square root of, I should leave this all up whenever algebra 2 comes in next spot. And so they come in and go,
So you said
are y'all ready to learn?
after 4, you said
Right, that's right. So 2.5, and then I would also do the 3.5, and then you stop. This one, remember, I set it up easy for myself with a width of 1 each time, so that I would just multiply everything by 1. But don't forget if that width was not 1. And I really, really hope if we plug this in on the calculator, we would get about 268, because that's what they got. That's with the pi. Yeah. We would just do units cubed because we weren't getting units. Oh, yes. No, y'all should have been in here.
I'll take credit for him.
Yeah. One is the width, but we doubled it because we only did half the sphere. So to account for the other half of the sphere. Oh, y'all want something from me now? Since y'all chose not to.